Alright, so here we are on our next section of notes. If you're following along in the Cornell style format, again, you can write your objectives in the essential question there, and then you can also list that our next topic is measuring and constructing segments. When we talk about measuring, we're not necessarily getting out a ruler today, but you are in fact talking about the length of what a segment could actually be, especially based on the fact that two lengths of it would make the whole at a midpoint. So, either way, here we go. The first thing that we're going to talk about is distance. Distance between A and B is the absolute value, meaning that it will never be negative. Alright, so you will never have all of a sudden a negative distance. I'm not sure where you're going, but nowhere that I know of. So, absolute value means a positive number, and it's the difference of the coordinates. So, if you actually had a coordinate grid, versus in this case just a two-dimensional segment or line, you could in fact, as you've probably seen with slope or distance formula, all you would do is subtract the components. But in this case, distance, we have to be very particular about it because distance is also known as length. And for absolutely no reason that I can come up with, a lot of times I'll say things like use the distance formula or use what formula would you use for length, and for some reason you can't put the fact that these two are interchangeable words. So just remember that distance is length, okay? And if you want to note the length, notice right here that all you do is either write word length, or notice that instead of having a segment up above AB, if you take that segment away, you now are actually being told that this is a length or a number. Alright, so that's the idea here. Again, distance is whatever the length is between A and B, and that's an always positive number. And to find the distance between this A and this B, all you need to do is write AB, but with no line or segment above it, and it's just going to be the distance. If I had a ruler, I'd measure it, but the idea in this case is actually that this is probably found algebraically. So, moving on, the next thing that we're looking at here is noted very poorly, so I'm going to kind of erase this. The idea is that we're looking at congruent segments, and so we are looking at this symbol, which is an equals, with a little tilde at the top, versus if we're talking about this symbol here. Okay, so this one here actually means congruent, and this one means equal, which of course we've seen before. The problem is that congruent is used with shapes, and equals is used with numbers. So the idea here is that if we are talking about segment PQ, that is actually going to be congruent to segment, you don't have to put the dots at the end, RS. Okay, and so notice that I've used the congruent symbol because I'm talking about a shape. But let's say that I actually knew the length, or eventually know the length. If I want to write PQ, whatever that distance is as a number, and I don't draw that segment above it, I can then say that it is equal to RS. Because these both represent numbers versus these both represent actual objects or shapes. Okay, so another way, other than using your symbols here when we're talking about some equality, you can also use tick marks. So the idea is that without having to say, for instance, this length is 10 meters and this length is 10 meters, if we don't have time for that, we can actually go ahead, and since we don't necessarily know the length, but we do know that if it was there, it would be equal, you put a tick mark on the object, okay, usually a segment. If you happen to have more things that are equal, you can't just use one tick mark on each thing. So you can actually double up, and so whatever has 2 tick marks is equal to the thing that has 2 tick marks, and you can use literally as many tick marks as you need. I've only really used up to 4, so it doesn't really go past that, but those are your tick marks. The next thing here, and we've got some interesting moments going from our previous slides to this, so this, for instance, here should be somewhere, so I will draw it where it needs to go when it comes up. Okay, so congruent segments that have the same length. This is actually what I just did in the previous slide, so we don't even need to clarify where all of those things go. This is just the book's definition of each of those. So the next one here, let's say that you are given a segment. What does it mean if a point is between 2 points? And that would mean that they are collinear. And we did talk about that in the first section of notes. And so if you have a point between 2 points, it does in fact have to be collinear or on the same line. Okay. The next question here is, what does it look like if a point is not between others? And so that would be non-collinear. Yes, that is a word. But again, the idea is that it's not on that same line. So there would be 2 points that are, and 1 point that is not. Maybe it's on the same plane, but it's not necessarily on the same line. All right, after that, we do have a postulate. Remember that from our first section of notes. Postulate means that it is something that is accepted without proof. But it turns out that segment addition postulate, really simple, means that if you have one segment and another segment that form a line eventually, you can actually add the segment pieces together. So for instance, if this was segment A, we're going to do an A here, B, and maybe we had M here in the middle, I could say that AM plus MB, so this piece plus this piece, equals the entire piece. So that's all the segment addition postulate says is, hey, guess what? You can add segments. Okay. Here are the official definitions of between. So again, here's between. They lie on the same line, again, collinear. And then here's the idea that I was talking about with apparently different letters. So we have A, B, C this time. And the idea is that AB, the piece on the left, could add to BC, the piece on the right, to end up with the entire piece, AC. All right. Next thing that we are going to talk about is bisecting and midpoint. Turns out bisecting happens a lot more with angles. So we will be talking about that. So angles usually. But other than angles, it can be used with segments, and just the idea is that it cuts whatever the object is in half. After you talk about bisect, a midpoint seems to cut it in half as well, but it's actually just at a point, okay? So you can bisect a plane, for instance, okay? You can cut a plane in half, and you can bisect a segment. But a midpoint is actually that dot in the middle. So you cannot, for instance, find a midpoint of a plane. That would be weird. Okay. So a midpoint is a point on a segment. And it is halfway between endpoints. Maybe I should write the rest of that word. Halfway between endpoints. The next page is going to be your actual definitions, but again, if I bisect something, I've cut it in half, and if I have a midpoint, of course it's a point, not necessarily a cut, but a point that is halfway between. So here's your definitions, if you want to write those down, pause the video. Alright, next piece here, this line that is right here, should actually be over here. So as the PowerPoint was transferred over to this app, it kind of made all the extras go somewhere else. So this first piece here is just identifying what it is that they are trying to get you to do. So first of all, this right here is the picture. I know it doesn't look like a picture, but from this we're supposed to draw a picture to represent it. If you don't draw a picture in your geometry problem, you're probably going to kind of miss the visual of it. So we've got a segment, okay, and that's what it says right here as the segment EF. And so I'm going to put E over here, F over here, and then I'm going to note that D is the midpoint. So I'm going to put something in the middle here. Now again, if I drew this really ugly for some reason, the idea is that I would know that this segment piece and this segment piece are the same. And so how do I make something the same even though I may have drawn it awkwardly? I would put a tick mark. Okay, so that's saying that from whatever point to whatever point that's surrounded by this tick mark is going to be the same as from one tick mark to the next with the singular line between it. Alright, then we go through and we notice that it also says that ED is actually representative of the measurement 4x plus 6. Now that is not necessarily a very helpful measurement, except that the fact that we are going to actually solve algebraically. So then the next piece is that D to F is 7x minus 9. Now you may say, okay, well we kind of need to know the whole thing in order for the piece plus the piece to equal the whole. But it turns out we don't need the piece plus the piece, we actually just need the two pieces because they're equal. Remember that tick mark that we made said that these two are equal pieces, and so we don't need this whole thing. Instead we can just say that ED equals DF, so therefore 4x plus 6 should equal 7x minus 9. If we do that, we'll be able to figure out what x is algebraically, and then we can plug it in order to answer the question, which says we need to find the length of each of the pieces. So algebraically, we're going to solve that 4x plus 6 equals 7x minus 9, and this is why geometry comes after algebra. We will be doing a lot of algebra in geometry so that we can maintain our knowledge of it before we move on to the next section. So I'm going to add a slide here. I've never done that in the middle here. Let's see if I can. Nope, so I'll just skip. So 4x plus 6 equals 7x minus 9. So here we are. 4x plus 6 equals 7x minus 9. And I'm very bad at remembering things, so let's go back. 4x plus 6, 7x minus 9. Okay. So we're going to go ahead and algebraically solve this. Whatever way it is that you solve something algebraically, combining like terms and things like that. When I do one of these problems, I will usually move the smallest number of x's over to the other side. So this positive 4x is going to be moved over to the 7x. Those two will cancel and leave us with a 6 on the left side and a new value of x's, so 3 of them, minus 9. Then we get to put the numbers together, so the positive 9 moves over here. And then we realize that we have a nice value that can divide into 15. So we'll divide both sides by 3 and realize that x is 5. So if x is 5, going back to the previous page, if x equals 5, plugging that in here means that we'll have 4 times 5 plus 6. And 4 times 5 plus 6 is 26. And so it looks like the measurement of ED is 26. The other piece, of course, is going to be 26 as well, unless you don't understand that these are the same. So technically I could plug in 7 times 5 minus 9 and get 35 minus 9, which is 26. Or, because we are a little smarter than that, we can say, ah yes, they're the same, so DF is 26. And then, of course, the entire thing together is going to be both of them. So EF is going to be 26 plus 26, so 52. And so as you're looking through this, one thing that happens with geometry is that you might think that this is the answer, and you're like, woohoo, x is 5, but we are no longer in algebra. We are in geometry. And so because of that, you're actually looking for this last piece, where some sort of segment has been found, or an angle, or whatever it happens to be, by plugging in what you found. So this is not quite the answer. This is the answer. All right. This last section here is asking you if you can kind of recite what we've just gone over. So the objective of this lesson was hopefully that you could use length and midpoint of a segment to figure out how to find an answer. So again, finding x with your algebra and then plugging it in to find your geometry lengths. Looking through here, midpoint. Remember, it's a point in the middle. We also have distance, which is a length. So those are those interchangeable words. Understanding that segments can be congruent, meaning the same length. Congruent is just another word of saying equal. Between would mean on a line. Bisect would mean cut something in half versus existing on the middle. And then we have segment bisectors, which again is just a bisector of a segment, which would cut it in half. So those are some of the pieces that hopefully you got from these notes. And again, you can redo the example on your own if you need some practice. Or, of course, we will have practice with the assignment that will be posted tomorrow.